Okay, so in this video, we will determine whether the following infinite series converges or diverges. So if we look at the terms of the sequence that we're trying to sum, sine squared of n over n to the 7, as n goes from 1 to infinity, clearly the terms of our sequence, an being the original sequence, are clearly non-negative. Sine oscillates between negative 1 and 1, but being squared makes it non-negative. N to the 7, again, n being a positive integer, makes it also positive. So every term of our sequence is at least non-negative. So this means that if we expand this out, I will use a shorthand an instead of writing out the terms explicitly. We get a1 plus a2 plus a3, and so on. We have an infinite series, trying to add these infinitely many terms as n goes from 1 to infinity. Because the terms of our sequence are non-negative, as we keep adding more and more terms, the result of our summation will naturally get larger and larger and larger, right? As you sum more and more positive terms, the result of the sum grows. And when something systematically is increasing, there are only two options. Either it increases to infinity, therefore the series diverges by blowing up to infinity, or if it does not blow up to infinity, then it remains bounded. So there is a cap to how large this can grow, and if this is bounded, you can again visualize this on the real line. Say there is an upper bound u for the result of the partial sum. So you have a 1, then you add a 2, add a 3, and if there is an upper bound, then there will be a least upper bound, and as you keep adding more and more terms of the sequence, the series will converge to this least upper bound, call it the limit. So again, we have to determine whether this infinite sum of positive terms will either increase, blow up to infinity, or if it does not blow up to infinity, it will be bounded above by some positive constant, and there will be therefore a least upper bound, the smallest possible upper bound, and so this result, the result of this infinite sum, if indeed is bounded by some constant, will have to converge to the least upper bound, the smallest upper bound of this infinite series. So how do we prove that this series either blows up to infinity or that it remains bounded? Well, this comes down to the intuition. And the intuition of the comparison test is to attempt to compare a complex looking series to a very simple either p-series or geometric series. So the first and most important step is the intuition. So what are these terms roughly like when n gets large? Well, as we've just said, sine of n is always between negative 1 and 1. So sine squared is always between 0 and 1. If you square something that is between negative 1 and 1, you get something between 0 and 1. And again, this will oscillate, sometimes closer to 0, sometimes closer to 1, sometimes anywhere in between. So if we use our intuition, because this is between 0 and 1, we can treat this roughly as a constant. We can say it's about 1. Maybe a little smaller, but it's roughly 1. And now the intuition kicks in. The terms we are trying to sum, an, will be roughly on top about 1 over n to the 7. So you can see that although the terms here are rather complex, they are about of the type 1 over n to the 7. And then this is when you can see that the original series, although it looks quite complex because of the sine squared on top, this is roughly a familiar p-series, where p is equal to 7. and 7 is larger than 1. And we know that when we have a p-series where p is any number larger than 1, the given p-series converges. So we have the intuition. This complex-looking sum is about the p-series where p is 7, which converges. So this infinite series, by our intuition, should converge. Therefore, it should be approaching some unique positive number. Therefore, it should be bounded. So we now have our intuition, our objective, which is to show that this series is bounded above by some constant. If it's bounded above, if it cannot grow past a certain point, then it cannot blow up to infinity, and so it will be converging to some positive number. So to prove that something is bounded above, right, that it does not blow to infinity, we have to show that the original series is smaller than or equal to a convergent series. And this comes from the intuition. We will prove that this infinite series is bounded above, so smaller than, some finite number. Well, we can already use what we've done before. Sine squared of n oscillates between 0 and 1, but is always at most 1. So we will replace sine squared of n by its maximum value, therefore make the resulting series larger than the original, as we've made the numerator larger. We've kept the denominator the same, so the inequality is valid, and as we've just said, this infinite p-series converges as p is larger than 1, and so this means that this, of course, is some real number, therefore is finite, strictly less than infinity. Right? That's what it means. When we say an infinite series converges, it means that if you sum all of these infinitely many terms, in the end you get a real number. And of course here we're summing positive terms, so is a positive real number. Well, this proves that this series is smaller than this number, say u. So now we have an upper bound in u. We can write it explicitly as this convergent infinite p-series. And again, because the initial series is bounded above by this number, there is a least upper bound that the original series will be getting closer and closer and closer to. So this infinite, rather complex looking series will be convergent by, of course, the comparison test. And that is our conclusion.